Assalamu alaikum Qtabiyani Khoshawis. Previously we've learned that Basha Gutman, if an object is at rest, obviously the net force on the object will be at equilibrium. And what does exactly will this mean, Basha? If an object is at rest or at equilibrium, the net force on an object will be zero. And that is clearly Newton's first law of motion, we could say, Basha. So let me give you an example of what we say here. Let's say we have this a surface, and here's an object, a box, Basha. This box is not moving. All right, so if it is not moving, can we say there is no force acting on the object? No, because there is always gravitational force, we can say Fg, and there's F normal, which is by the surface on this object. But if these two are equal in magnitude and opposite in direction, clearly then these two would balance. We can say on y-axis, we can say Fy, right? That is, we can say Fg plus, or we can, let's just say F normal plus minus Fg. Basha, these two are zero. If that is zero here, that would be the total force acting on the object. If the net force acting on the object is zero, then this object stays at rest. It's not going to move down or up. It's the same thing if you apply a force, let's say on right and left as well. Let's say we apply a force of 10 Newton to the right, and then there is a force of 10 Newton to the left. Now these two forces, of course, cancel out, right? So if that is the case, then the object will stay at rest. At this point here, then we can say the object is at equilibrium, Basha. All right, so this is what happened here. But what about for charges here? When will a charge be at equilibrium? We know that if the electrical force on a charge is zero, then the charge will be at equilibrium. What do we mean by this? Let's say here's a positive charge and here's another positive charge. There is a negative charge in between the two, right? Now this negative charge, of course, it is going to be attracted by both of these two charges, right? So, but if the forces, because there is a force between these two, right? There is a force between these two here, and then there is also a force between these two as well. Now we can give them some names here. Let's call this one Q1 and call this one Q2, right? And call this one Q3 as well. So there is a force between, we can say Q1 and Q3, Basha. So that, of course, we can say F bubbling on 3 by 2 here. So we'll say F 3 by, F, the force on charge 3 by 2. This is charge 3, Basha. F by the charge 1, Basha. By charge 1. And then the other side here, Gutman, we can say this is again between these two here, because this one is attracting the charge. So we'll say the force on 3, but this time by 2. Watch this. If these two forces are equal in magnitude, Basha, and opposite in direction, you could just call them the force that is to the right and also the force that is to the left. This is the left, the other one is right. Right? If these two forces are equal in magnitude and opposite in direction, then do you think this charge will move? Let's say at this point, the answer is no. But will this charge always be right in the middle between the two charges? No. Okay, and how or why is not? Because most of the time, bubbling, if one of the charges is larger than the other charge, clearly there is going to be a stronger force between the two, right? So let's say this is one of the charges that we have. This is the negative charge, and then this is the, let's say, the other charge in here. Clearly, there is a bigger charge in here. That means it's going to be a bigger attraction force. So in order for the two forces to be equal, then it has to be the twin blend, the smaller, or the charge that is in the middle will always have to be closer to the smaller charge. Why? So that this, because for this force to be small, then the distance has to be very large. So for this force, for the force between these two to be small, the distance has to be what? The distance between the two has to be large. So force that is inversely proportional with the square of the distance between the two. So that these two forces are equal to one another. You might not need all this. So what exactly do you need at this point? Later, you need 2 points, Basha. We, like most of the time, we have 3 charges, Basha. So let's call that Q1 and then Q2 here. And then there is a charge in between the two, Basha. So what exactly do you need to do? So we can call this one Q3, Basha. Q3. But man, this Q3 will be at equilibrium only if the forces that are to the right, to the left, it is equal to the force that is to the right. Now there is a force between the two. there's also, or there will be a force between the two as well. So we can say if F3, all right, bubbling 1, it is equal in magnitude and opposite to the, let's say opposite to the force between 3 and 2. If that is the case, then this charge here, it is going to be at equilibrium. But there is one more thing here. Like, we want to know where exactly we should put Q3 so that is going to be at equilibrium. So this is the first equation that you need to use, Basha. The second thing that you need to do, for example, most of the time, Yan Bublin, the distance between the two charges, Q1, Basha, and Q2 will be given, Baba. Right? Q2 will be given. So here is charge 3, right? So let's say the distance between the two is 2 meters. Let's just say, Basha. We don't know where exactly we should put Q3 at this point here. So أما ديستانسي أولاد كنا P باشا ديستانسي لاكي دي كده بيتتسا هم زارة دي بيت أو ديستانسي كواهيتمان it becomes 2 minus P. أو زشرني 2 بيتن. It could be any other numbers. Kata, what that will be the second point you need to do, Basha. Regarding the distance, good man. But distance يقلع كان دكينا P, you can make it distance D for D, you can make it R, you could make it any other letters here, Basha. So we choose P as a distance here. If I have a distance that is 2 meters long, Basha, 2 meters long. If I take a section off, Basha, let's call it P. What is the remaining distance that is left? Can I say 2 minus P? Yes, that is exactly what we're going to do, Basha. Kata distance ilachi, debita P ilachi, dika debita te, debita o distance ko height man, so whatever the number minus P. So let me give you, for example, an example. So see, or maybe solve a question, see how it is done. All right? So just remember this too, Baba. Gutman, these are the only two things that you need to do. Basha, Gutman, you could start with the distance if you want to. Basha, Gutman, we will always have 3 charges, Q1, Q2, Basha, and there is a charge that is in between. Gutman, distance yek, babbling la chibani 2 charge can will make it P. It doesn't matter if it is this side or the other side, doesn't matter. Whatever the distance that is given here, Basha, so let's say 3 this time. We'll just say 3 minus P. So whatever the distance given, that'll be minus P for the other side. That is the first step. The second step, Gutman, these two forces must be equal in magnitude and opposite in direction. So we can say 3 by 1 on 3 by 2. Now all you have to do is just use Coulomb's law and then find the distance. That's the only thing you need to do. All right, let's solve a question and see how it is done. Basha, now these are what it is. Gutman, objects at rest or equilibrium with zero net external net external force. Gutman, electrostatic equilibrium occurs and happens if the net electric force on the charge is 0. Gutman, to find equilibrium, determine where the electric force from one charge equals or not to the other one. So by using Coulomb's law. The second thing, Gutman, or that'll be you could say the distance here, where the electric charge, and then use Coulomb's law to set the forces equal and solve for the distance between the two. نتواني استفادة لستريتي بيبكي من هاد زارك أجر قوتي بابا التشارج وشتانا ما نهبو لا تشوكا بي لا كيديكش distance كهر سندك بو minus p, and then you could just answer the question. But example man here, let's solve this example together and see how it is done. Basha. All right. So what exactly do we have? Baba Odu pointish labir bitin labirian maka. Got delay three charges lie along the x-axis. Basha my x-axis man here laga y-axis man here wania. Later 3 charges lie along the x-axis. Yani listed Babylon x-axis, not y, just on x-axis. 3 charges, Basha. All right. So it says one positive charge Q1, which is 15 micro at x equal to 2, Basha. So we can consider this, for example, to be x origin or 0 here. Later, Gutman, charge Ekman, you can call this one Q1, all right? Q1. Charge Ekitana, it is 15 microcoulomb, but it is at x equal to 2 meters. So here, the distance we can say, starting from the origin here, all the way it is equal to 2 meters. Basha, that is the first charge in here. And you can write down the value for the charge and the given one. The next thing says, and another positive charge, Q2, which is this much, but it says at the origin. Where's the origin? That means origin is basically the axis where it is, we have x and y 0, 0, and yeah, that is the origin. So this is going to be our second charge here. Kata, this is the second, charge. So we can call this one Q2. But it is at the origin where the x is 0. The distance between Q1 and Q2 is 2 meters. Here's the next part, and you can write their value too. Basha, it says, so this is with mano value Q1 wash Q2. It says, at what point on the x-axis must a negative charge Q3 be placed so that the resultant force on it is 0? I got low keyword AB, you can underline this one for yourself. So the resultant, where should we place a negative charge in between the two, where the net electrical force on that charge is 0? The value for one of the charges is 15. This charge, all right, will always have to be in the third charge, the one that is in the middle, or we put them in between. It is always has to be closer to the smaller charge, Basha. So at this point here, we can say this is Q3, which is negative, all right? So how far is it? What exactly do we do here? We'll make the distance between one side P, Basha. So this is P. Now the distance that we have, it is the total distance is 2. 2 minus P. Basha. 2 minus P. That'll be the distance. Now, that is the first step. What is the second step? These forces must be equal in magnitude and opposite in direction. We can say that these charges both apply a force on 3. I will say the force on 3 by 2. Right? Or we can start with 1, doesn't matter, Basha. And then it must be equal in magnitude and opposite to the force on 3 by 1 here. Okay? So now all you have to do, just do the math. Force Coulomb's constant طبعا Q3 Q2 what is the distance? You can say the distance between the charge 3 and 2 بزود distance square. It is equal to K أو دارة Q3, because you can see that this force between 1 and 3, right? Q1 distance بين 3 and 1 square شباشة. Now of course these are the same, so we can cancel them out. You can see Q3 and Q3, I have them on both sides too. Kata Q2 is left. What is the value for Q2 now? The value for Q2, it is what is it here? It is 6 micro. 6 micro. 6 times 10 to the power negative 6. Distance بين أنسندا. We said that the distance between Q2 and 3, it is just P1, but square is P squared. All right, on the other side here, we have Q1, which is 15 micro, 15 times 10 to the power negative 6, divide by distance بين Q3, Q1, we said that is 2 minus P, which the beta square. Now, you can cancel out this micro and micro 2 here, so you can work it out. So the next thing that we have, all right, I believe at this point we don't need this anymore. We'll just use this now. Basha. So now all you have to do is just cross multiply. You can see that, Basha. So we can say 15 times P squared. That's it. That's 6 times 2 minus P and we squared. Now, of course, if you divide both sides by 15 here, or you could just move 15 here to this side, Basha, that'll be what? That'll be P squared, 6 over 15, 2 minus P squared. Try to take the square root for both sides because we want to find P here. Right? Once you do this, good man, P dominator, 6 divided by 15, 2 minus P, it came out of the radical here. So now I want you to use a calculator, all right? Find this number, you can just multiply it into the bracket here. So one more time, طبعا step is getting a bit longer, but it's nothing complicated. These are just math and not physics anymore. Only the first 2 steps are more physics, the rest are just simple math. So now we can say P, let's get a calculator and see what is this number equal to. Okay, so we have the radical of 6 over 15. The answer to that, it is equal to 0.632 and all that, right? So we'll just write 2 digits, 0.63 times 2 minus P. Now, all you have to do is just multiply this into these numbers here, right? So just multiply this into the bracket here. So what do we get now? So we'll say P, it is equal to 0.63 times 2. The answer is going to be 1.26 and then minus 0.63p. Now, of course, this is going to be we'll move this one to the other side here because p has to be with p and then numbers alone at one side here, you could say. Kata will say 0.63p plus there's 1p, right? Plus 1p, that is going to be obviously 1.6 equal to 1.26. Start this two, good man, 1.63 p, دكاترة said دكاترة 1.26. Now divide both sides by 1.63 because we want to find the value for p. 1.63, what is it equal to? P دكاترة, these two cancel out. 1.26 divided by 1.63, the answer is going to be 0.77, Basha, and then 3, 0.773. We can say 0.8 as well if you want to round it up to one, let's say, digits after the decimal, one digit after the decimal. So this is the value for P now. So if we go back to this one here, how far should this charge be from charge 1? Right, it has to be about 0.77 meter, Basha. What about the other side? If we ever want to, that would be 2 minus 0.77. That is going to be 117. Let's find out. 2 minus 0.77, Basha. The answer is going to be 1.23, Basha. So this is how far it has to be. 1.23. This is how far is going to be from Q1. It doesn't, you don't have to. So now we know that if you place charge 3 at a distance of 0.77 from Q2, then at that point this charge will be at equilibrium. So this is how you do that. يعني كاتبها بستيب كان تبو ستيب يكم قلت مان لا شيء distance كان كبي لا كدي كدبيت distance كهر صندق بو minus p. When you do the second step, قلت مان just write these two forces are equal in magnitude, باشا, and opposite in direction. So just equalize them. Babylon F3 2, it is equal to F3 and 1 here. So now just write their equations, cancel, simplify the equations, and then the rest just do the math, Basha, or that'll be simple math. All right. So the answer is about, we can say, if we round it up, it is going to be 0.877, but if you round it up, that'll be 0.8, of course, from Q2 here. It is the same idea. We're going to solve this one too, Basha. All right, let's just keep this one here. So what do we have here? It says we have a charge of 2, Basha. We have a charge of 2 times 10 to the power negative 9 coulomb. So we can call this one Q1. It says placed at the origin. So where's the origin? That'll be, you know, like the point where x and y is 0, 0 here. That is the origin. So this is Q1, we could say, Basha. Let's just keep this one here. So this is Q1. The value of Q1, it is 2 times 1, Basha. And another charge of this much, 4 times this, Basha, is placed at x equal to 1.5 meters. So there is another charge in here. Let's say this is 1, Basha. So this is 0, this is 1, this is going to be 1. Let's just say this is 1.5. All right, right away. So the total distance between, we can say Q1. So we can say the Q1 and this is going to be Q2. The distance between the two, it is just going to be 1.5 meter, Basha. That'll be the distance between the two charges. So I find the point between these two charges, yani where exactly between these two charges, where a charge of +3 should be placed so that the net electric force is 0, Basha. Where can we place the third charge, or Q3, between these two charges? And you can see here, all of these charges are positive this time here. All right. So that this, or the electrical force between where this point is, or the net electrical force is 0. So what exactly happens here? This charge is trying to push this, the third one, away, and this one is also trying to push it away. So at some point, these forces are equal in magnitude and opposite in direction, so the charge will be at equilibrium. Gutman, what are the first step you need to do, Baba? قلت مع لاك للديستانس كان كبي باشا لاك ديك whatever the distance is that distance كتسنى 1.5 وانا كاتدلن 1.5 minus p. This is what you need to do يعني nothing more than that. أو ديك دمينتها قلت مع equation كان equalize كا باشا. So now we can say we have three charges. We can say the force on Basha 3 by 1, right, must equal to the force on 3 by 2. Now the rest just do the math. Good man equation K coulombs constant because Q this is 1 and 3 when Q3 Q1 over good man distance بين 3 and 1 squared لكن دي كده كاتا K دوباره good man this is between 3 and 2 كاتا Q3 Q2 the distance between 3 and 2 squared. Now these are of course now you can cancel some of these. These two cancel out, Q3 and Q3 cancel out. So now all we have what is left is Q1 over the distance, Q2 over the distance, and that's it. So what is Q1 now? So Q1 it is 2, when yeah, 2 times 10 to the power negative 9 coulomb. Now distance بين 3 1 we just call that P, but it is squared one, yeah, so P squared. لكن دي كده بتسا Q2 it is 4 times 10 to the power negative 9 divided by the distance between the two لكن دي كشمان كده P لكن دي كشمان كده 1.5 minus P أوش همي squared. Now all you have to get man you could simplify even further أو دو cancel دبنو دو باركاتا you could cross multiply now باشا, and then of course we could just save some space here. But man, this one, of course, you can see that would become 4p squared. They got 2 times 1.5 minus p squared. Now, of course, you could move or divide both sides by 4. So you could move this one here. That would be p squared. It is equal to 2 over 4. 1.5 minus p squared. So, start take the radical for both sides. But man, with the beta p. أوش دبيتا radically 2 over 4 باشا. What is left أو يديكش دبيتا 1.5 minus p is that square كنما. Now find the square root of 2 over 4 and let's see what is it equal to. 2 over 4, the answer is equal to 0.707 باشا. كاتا p دكاتا 0.707 multiplied by this one will an open bracket 1.5 minus p. ستنها math باب step كان which بس ما كنت عندك زيادة ليرة, but this is nothing physics, it's just math. You can multiply this into the bracket p the beta. What is 0.707? 0.707 times 1.5 or the kata 1.06 باشا. 1.06 minus 0.707p باشا. So that p can move to the other side. Later 1p or يديكش 0.7 كاتا the beta 1.707p or the kata 1.06. So that divide both sides by 1.707. P كده kata 1.06 divided by 1.707. Let's find out what is it equal to. 1.06 divided by 1.707, the answer will be 0.62. 0.62 باشا. 0.62 meter. Kata P, which is the distance between Q3 and Q1, or distance that بيتم it has to be 0.62 meter باشا. I can tell you that 1.5 minus p, then you can find that. This is how easy it is. Basha, good man tanha, do step yakami bzana, how you put them, and then the rest is just simple math, baba. It might sound a bit complicated, seem a bit complicated, but it's nothing special. بسارش عن an idea تاني حليك حزم نبو بسارش لو حل كان بسارش يزور جوانا باشا. An electron is released باشا above the Earth's surface here. So here's, let's say, the Earth's surface. Here's an electron, Basha. This electron is released. It's the same as dropped. So if this electron is dropped, clearly force of gravity tries to pull it down. Yes or no? So there is a force of gravity downward here. All right. So force of gravity, we can say, Fg, is downward here. Look what it says. It says a second electron is directly below it, Basha. Below that electron, it exerts just enough of an electric force on the first electron to cancel the gravitational force on it. The question says there is another electron below that. Obviously, these electron, they repel one another. But this electron, it applies enough electric force, Pasha, just enough to cancel the effect of gravity. يعني أو electric force ودكاتنا أو electron تيدي كفال نبيتن. يعني it's almost like keeps it levitating, keeps it in the air without letting further. Basha, let's find the distance between the two electrons here. طبعا بسارة شي زور جوانا. Basha, how do we find this one here, Baba? قطمان in order استعليرا F جيكا قطمان لو خواري F electric لو سريع ونيا قطمان in order to cancel the effect of gravity يعني دبي أو electric force دبي بقدر F جيكا جوربيتن so that these two can cancel out ونيا ما بشتري باس مانك قطمان when will two forces balance one another if they're equal in magnitude and opposite in direction. I would say it could be, for example, how we were talking about gravitational force and normal force. I get F G, F normal equal, but then the object will not go up or down because the net will be zero. So here we have electric and gravitational force. The line, electric force, Basha, must be equal in magnitude and opposite to the gravitational force between these two electrons, obviously. But what is exactly electric force equal to? It is equal to Coulomb's law, Q1, Q2, and these are the charges of electron divided by the distance between the two. Distance like a square issue, Basha. The question says find the distance. On the other side here, we have gravitational force. When in gravitational force here, you could just write mg at this point, Basha, because that would be the weight of this electron here. But later mass electron man paste Baba, I got no khalibitim. All right, so now let's just plug in the numbers. So this is the unknown one here. Can I just, for example, move this one to the other side and bring mg here? Yes, we could do that one, yeah. Or we could just, what is it called? Yeah, the same thing actually. All right, so let's just say r squared, dekata k, q1, q2 over mg. بس أول ما يجي electron بابا قاعد زود باشا. Now all you have to do just plug in the numbers. K, Coulomb's constant, but man 8.85 times 10 to the power negative, I keep saying negative, positive 9, Basha. Charge electroni baba, we know that it's 1.6 times 10 to the power negative 19. هذه charge electron كيديكا عين نشتا 1.6 times 10 to the power negative 19 دوباره. So divided by massive electron, which is 9.1 times 10 to the power negative 31. All right, and then times gravitational acceleration, which is going to be 9.81. We don't write any negative in the equation, so once you do the math, right, you will get an answer, Basha. But then this is r squared. You will have to take the radical for both sides. Then r, it is equal to 5.07 meter. This is the distance between, or the distance will be between the two, even though this number seems a bit big, but it doesn't matter. Whatever the answer you get, that'll be it, and this is how you can do that. Kata, what is the main idea in this question, Baba? They're good man to cancel to the effect of gravity, Kata, the electric force equal between legal gravitational force and bubble in magnitude equal bin Basha. These are equal in magnitude but opposite in direction. Equation now you can find the distance between the two, which we just did. Basha, the next thing that we have, it is electric force is a field force. There are two types of forces. One, contact forces and field forces. For contact forces, there must be a direct contact between the two in order for the force to act. Let's say you want to open the door, without you touching the doorknob, like there's a physical contact here. Can you open the door? Can you open the door? No. So these kind of forces are called contact forces that require a contact. But on the other hand, we have field forces like gravitational force. You drop a pen, it falls even if there's no contact. Magnetic force, or now we've learned about electric force. So these can affect, can attract or repel even without a direct contact. So these kind of forces, we call them field forces. So electrical force is one of them, and of course is stated by Coulomb's law. All right. So we can say a field force, it is a force that is exerted by one object on another without a physical contact. For example, or examples include Coulomb's force, which is electric force, and gravitational attraction, we could say. Gravitational attraction is also a field force. All right, so you can see, for example, these fill lines. By the way, these fill lines are not real. These are just visual aids to help you understand better. These are, of course, these to attract one another, these to repel one another. What is the difference between this and this according to the line? Huh? You can see there are more lines here, which means that this charge is, or there's a huge charge in here, or it has a big amount, so that there is a strong attraction on this negative charges here. Got that? We have a few questions here. How is the Coulomb's force similar to gravitational force? Electrical force, it is basically the force between charges, but gravitational force is the force between masses. But the similarity, these are both inversely proportional with the square of the distance. Inverse legal square distance. How does the electric force differ from gravitational force? We just said that. Electric force, it could be attractive force or repulsive force. It is between two charges. But gravitational force, it is only attractive force, and it is between masses. These are electric between charges. For gravity is between masses. How does the strength of electric force compare to gravitational force? Example, electric force is way stronger than gravitational force, especially if it is at the atomic level. Force compared to gravitational force. Can a small amount of charge overcome gravitational force? Prove or provide an example. Yes. Okay, a small amount of charge can still overcome gravitational force. You rub a balloon, it can stick to the wall, even though the rubbing process only creates a small amount of charge, but now the balloon can stick to the wall, which defies the force of gravity. It doesn't let the balloon to fall downward, right? So that is a proof that electrical force is stronger. If not, you could rub the balloon with your hair. You can see that it makes the hair to stand on its end. That is also another gravity pulls the hair down, but the balloon can make them stand on its end, which means that electrical force is stronger even by a small amount of, or small rub. So Coulomb quantified electric force with a torsion balance. What exactly do we have? Coulomb, he was the first person to quantize the electrical force. He was the first person to find out how much electrical force, let's say, there is between two charges. And also he also invented the inverse square law too. So what exactly did he do? He used this balance to measure the force between the two. So what is this balance made of? These balance made of two spheres that is on uninsulator material, separated by an insulator dash. As you can see here, this sphere here, so first of all, this sphere is charged here, and then do I object take baba charge, and then this two, of course, are going to, let's say, oppose one another or repel one another. By knowing how much it deflects and the angle that it deflects, you can find, or he could use this method to measure the force between two electrical charges. Coulomb, he was the first person to quantize electrical force, and also he was the one that inverted the inverse square law. What did he use? He used the torsion balance. Now the next thing that we have, and section review here party C. how many electrons مادام باسی how many electrons دكا وبيشتري equation كمان هو زعم لبيتان معينة. The small glass is rubbed with silk gains a charge of this much. We can say this is Q1, which is micro means 10 to the power negative 6. The glass ball is placed 12 centimeter. Now the distance is 12 centimeter. Centimeter needs to be converted. How do you convert centimeter? Divide by 100. أو كاتي دبيته 0.12 meter. Centimeter is gone now. From a small charged rubber ball that carries a charge of this much. We have a small glass. There is a glass. There's a small glass ball, and then there is a rubber ball. And these are the charge of each one of them. You can call this one Q2, and this is the distance between the two. What is the magnitude of the electrical force between the two? What is the magnitude of electrical force between the two? So we can say part A, write electrical force equation. K, Coulomb's equation. Q1, Q2 divide by the square of the distance between the two. 8.85 times 10 to the power times 10 to the power 9 times charge يكم is 2 micro ونيا micro negative 6 charge دوام it is 3.5 قلت ما negative كان now equation electric force ينانوشن times 10 to the power negative 6 باشا and then divide by the distance قلت ما distance كيف كم 12 divided by 100 that'll be 0.12 وش دبيت square now part يكم يعني electric force كده كاتسن it is we're supposed to equal to 4.37 Newton since it is electrical force. That is for part A. Part B is the force is this force of attraction or repulsion. One of them is positive, right? It is positive 2. You can see that it is negative 1, yeah. So if we have positive and negative, what do you think the nature of the forces will be? Of course, it's going to be attractive. Attractive force. What about part C? I like part C too. It says how many charge or how many electrons has the glass ball lost in the rubbing process? Basha, how many electrons? Whenever the question says how many electrons, Baba, or the excess electron okati, we have one equation, good man. So this would be n. All right, that is going to be the number, Basha, number of what? Number of electrons. Number of electrons, Basha, that is equal to Gutman, the charge on the object divided by the charge of the electron here, Basha. So Gutman, the negative that doesn't matter, Basha, because we just want to find the number of electrons here at this point. So it says for the glass ball lost one, yeah, if it is going to lose a charge, obviously it is going to then we're going to use the charge for the glass ball. What was the charge for a glass ball here? All right, so glass ball, it was positive 2 micro. So this is the charge on the glass ball, 2 micro, 2 times 10 to the power negative 6 coulomb. All right, divide by the charge of the electron, which is 1.6 times 10 to the power negative 19. Then you can find this one here. So at this point, we can say, by the way, all right, so let's just forget that. So it is going to be 1.25 times 10 to the power 13 electrons, Basha. This is how many electrons the glass ball has lost to become positive 2 microcoulombs, Basha. All right, and this is how you do that. This was a very good question. Also talks about the distance, the electrical force between negatively charged paint, Basha, droplets and a positively charged violin automobile body is increased by a factor of 2. She increasable by a factor of 2, Baba, the electric force between the charges. And the force increased by a factor of 2. But the charges on each remain constant. How has the distance between the two charges changed? Man, agar equation Basha, what is the equation between electric force and the distance? There are inversely proportional with the square of the distance. Whichever is given, Baba, make that one, or you can, whichever that is asked or unknown, you can make that the subject. Stop Saraka. It is, increased by a factor of 2. So the force is 2. We can say 2, it is equal to, Babylon, let's just make it this one here, 1 over R2, because that's what the question is saying. Now, but we want R, or R is unknown. Can I just swap this to here? Yes. In this case, we can say R squared, the kata 1 over 2 here, Basha. But once again, we want the distance, not the R squared here. Kata, we'll take the radical for both sides here. We can say R, the kata 1 over the radical of 2, or you can say the new R becomes 1 over the radical of 2 times the old distance here. Basha kata, in order, ata forsa ka du jazat ka the distance ka, bo factor and this the become bibito by this factor, which is 1 over the radical of 2, Basha. This is how you do that. يعني شهادة واني ليرة excel أركب subject that'll be 1 over the force is that force كدوا نزيد أنا سكروتي لو أقرأ that is going to be the same thing. Basha. Wash persara chi tuan bo persara na baba the tuan and these are exactly the same shtichuainia. There is critical thinking. Kandala, what are some similarities and differences between gravitational and electric force? What some perturbatio man kadia man electric force can be attractive or repulsive, but gravitational it is only attractive. Basha. Electric force, it is inversely proportional to the square of the distance. Awasham inversely proportional to the square of the distance. Kata with the tuan similarity. قلت معنى electric force كان due to electric charges between positive negative 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 charges كاتا due to the charges. قلت مان force اللي كذي because of charges ليه اللي كذي because of the masses باشا. قلت مان electrical force is significantly يعني is a lot stronger than gravitational force. Gravitational force, it is weaker in comparison to the electrical force. All right, that'll be the end for this session, inshallah. Next time we'll talk about electric field. Basha, till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.